Welcome back, Focus Learners. I am so incredibly pumped for this explainer session because today we are playing the role of the alchemist. We are going to take your basic, everyday computer science knowledge and transform it into absolute gold standard exam evaluation. If you are aiming for those top-tier marks in your Cambridge exams, you have landed in exactly the right place. Today, we are completely demystifying Cambridge Syllabus 9618 Sound Representation and Encoding, and we are specifically zeroing in on the notoriously tricky area of sampling. Now, whether you're building foundational knowledge in syllabuses like 0417, 0478, 0983, 0984, or 2210, or you're tackling the advanced A-level 9618 curriculum, the examiners themselves consistently report that this is literally one of the most misunderstood areas in the entire computer science ecosystem. We constantly see candidates falling into the exact same traps year after year. Let me paint a vivid picture for you using a classic past paper scenario. Let's look at a typical 9713 or 9618 style question. Imagine two students taking the exact same exam. We'll call them Alex and Sam. Alex is brilliant at memorization. I mean absolute photographic memory. Alex overloads every single answer with raw computer science facts about sound waves, amplitudes, and frequencies, but provides absolutely zero analytical depth. It's just a wall of text. Sam, on the other hand, truly knows the concepts, but totally crumbles under pressure, rushing through the paper and completely missing the crucial command word requirements in the question prompt. Both of these students walk out of the exam hall feeling super confident, but when results day rolls around, their papers are just covered in red pen marks. Ouch. So throughout this explainer, we are going to look closely at their flawed answers, understand exactly why the examiners penalize them so harshly, and show you the exact blueprint to guarantee you secure those top marks.
So, let's address the elephant in the room. Why do students find algorithmic thinking and efficiency in sound sampling so incredibly hard? Honestly, it is completely normal if you've opened up a past paper, looked at a question asking you to calculate sound file sizes or analyze complex quantitation errors, and felt an immediate wave of panic. You are definitely not alone in that. The real struggle stems from the fact that sound sampling isn't just about rote memorizing definitions like sample rate or bit resolution. It is way deeper than that. It requires a highly complex blend of mathematical logic, hardware understanding, and procedural problem solving. When you are asked to evaluate the efficiency of a sampling algorithm or discuss the trade-off between file size and audio fidelity, the examiner isn't just testing what you know, they're testing how you think. Average candidates, like our friend Alex, just list basic facts. They'll write, a higher sample rate means better quality audio. End of sentence. But examiners want to know the why and the how. They want to see the underlying algorithms. They want to know you understand the data structures. In this session, we are going to provide the ultimate solution. We're going to decode those command words and ensure you never bleed those critical evaluation marks again. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's dive into this. Here is our structured roadmap for the day. We're hitting assessment domains, core principles, the procedural framework, critical evaluation, and finally, those juicy principal examiner insights.
Starting off with Section 1, Assessment Domains. This is the cognitive benchmark you are actually being graded against. Before you can even attempt to write a perfect answer, you have to fundamentally understand the game you are playing. The examiner is literally reading your exam paper with a very specific rigid checklist of assessment objectives in their head. Notice how clearly these three core cognitive domains are mapped out here: knowledge and understanding, application, and analysis. These form the absolute bedrock of the Cambridge exam structure, regardless of whether you are sitting for 0478 or 9618. Notice how the cognitive difficulty scales up dramatically. Knowledge is your basic recall. Can you simply define what a sample is? Can you state the Nyquist theorem? Application forces you to take that static definition and actually calculate a sound file size for a specific, perhaps totally unfamiliar context provided in the question. But analysis, wow, that is where the real magic happens. That is the gold standard. That is where you have to evaluate the trade-offs, like balancing high audio fidelity against extremely limited storage capacity on a specific device. The syllabus explicitly emphasizes that top-performing students exhibit connected conceptual understanding that is completely transferable. To hit this, we use the Peel framework: point, evidence, explanation, and link. If you only operate in the first row of this table, just dropping facts without Peel, you are playing Alex's game, and you will absolutely cap your grade at a C or a B. We want A stars.
Let's move right into Section 2, Core Principles. This is the theoretical architecture required to actually score high marks.
We need to draw a very sharp contrast here between superficial breadth and analytical depth. This right here is the fundamental difference between an average candidate and a top-tier candidate. Let's go back to our two students, Alex and Sam, and watch a little transformation. When asked to evaluate a sound sampling approach, Alex writes a massive, sprawling paragraph listing every single fact imaginable about sound. Analog to digital converters, amplitudes, frequencies, you name it. That is superficial breadth. Sam tries to answer too quickly, ignores the command word evaluate, and just states that higher bit depth equals a larger file. Both of them lose major marks. Why? Because the assessment framework prioritizes structured, evidence-based reasoning. This is where we apply that Peel framework I mentioned. Instead of a messy fact dump, you make a clear point about the sampling rate. You provide evidence directly from the scenario provided in the question prompt. You give a detailed explanation of the technical mechanics, like exactly how quantization errors are reduced. And finally, you link it back to the command word. When you do this, those red pen marks transform into green check marks. This is our computer science success blueprint.
So, the crucial point is that the theoretical architecture of sound representation and encoding rests entirely on three pillars: precise definitions, causal relationships, and integration with other syllabus areas. You absolutely cannot treat sound sampling in a vacuum. It doesn't exist in isolation. A change in bit depth causes a direct change in quantization accuracy. That is a causal relationship. But how does that affect network transmission speeds if this particular sound file needs to be streamed live over the internet? Boom! Now you are making cross-topic connections between data representation and networking hardware. Principal examiner reports consistently highlight that candidates who reference cross-topic integration achieve significantly higher marks. It shows true mastery of computer science, not just basic memorization. Stop scrolling, subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel on your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, Section 3, the procedural framework. Let's talk about the exact technical methodology.
Welcome to our interactive workshop. For the next few minutes, we're going to actively apply these concepts. In computer science, examiners don't just want to see the final, magically correct answer. They want to see your brain working on the page. They use what we call the method mark strategy, where examiners award marks for your actual process, even if your final math is a bit wonky. Let's break down the linear progression of algorithmic thinking that Cambridge expects. Think of this as Challenge 1, the data scan. First up, step-by-step decomposition. If you are asked to design an algorithm to process a stream of sound samples, you must break the problem down into bite-sized chunks. Second, appropriate data structure selection. Are you storing these incoming audio samples in a 1D array? Are you using a linked list? You must justify why. Third, efficient code implementation. This means writing clean, logical pseudocode or program code that accurately reflects your strategy. And fourth, rigorous testing. By making your procedural framework highly visible to the examiner, you guarantee that even if you mess up a multiplication step in a file size calculation, you still capture the vast majority of the method marks.
And this brilliantly illustrates the exact operational sequence for tackling complex examination questions systematically. Consider this, Challenge 2, find the flaw. I want you to imagine a 60-second timer on your screen right now. Step 1, deconstruct the command word. When you look at a question, ask yourself, is it describe, explain, or evaluate? If you explain when you were supposed to evaluate, you lose. Step 2, extract relevant data. Pull the sample rate, the duration, and the bit resolution straight out of the text before you do anything else. Step 3, select your analytical framework. Are you comparing two things? Use Peel. Step 4, execute with clear notation and perfect terminology. If you see a flawed sample paragraph that just says 8 kHz is worse than 44 kHz, you should immediately spot the flaw. It lacks data extraction, it lacks framework, and it lacks execution. Identifying these flaws in your own work before the examiner does is how you level up.
Let's shift into Section 4, critical evaluation. This is where we separate the A-stars from the rest.
We are now heavily focused on the higher-order assessment objectives that differentiate the truly elite candidates. Problem-solving at this level uses a highly specific deconstruct, solve, evaluate framework. When you see command words like evaluate or discuss, you're actively expected to evaluate alternatives, compare different approaches, and make fully justified recommendations. For example, if an exam question provides a complex data table showing different audio compression formats, you must be able to extract the core trend instantly.
You solve the problem systematically, perhaps calculating the compression ratio for each, but then you absolutely must check for reasonableness. This is a vital step. Is your calculated file size realistic for a 3-minute pop song? If your math tells you the file is 4 terabytes, you've clearly missed a conversion from bits to bytes somewhere. Checking for reasonableness saves you from looking foolish. You then must justify your final recommendation based purely on the specific constraints of the system given in the prompt.
Okay, let's run challenge 3, speed writing. I want you to imagine a 30-second timer counting down. How do you write a perfect comparative analysis paragraph under immense pressure? Well, you use this specific checklist. You must identify similarities and differences. You must use comparative connectives, words like whereas, however, or in contrast to. You must support every single point with evidence from the data table and draw logical conclusions. Missing any of these elements leaves huge method marks on the table. So a perfect Peel paragraph speed written in 30 seconds would sound exactly like this. While both sample rates digitize analog sound, the 44.1 kHz rate captures more than double the frequencies of an 8 kHz rate. This higher rate significantly reduces quantization errors, yielding higher audio fidelity, whereas the 8 kHz rate, although resulting in a demonstrably lower quality output, creates a vastly smaller file size that is much more suitable for limited bandwidth transmission. Boom. Point, evidence, explanation, link. That is a perfect examiner-approved paragraph.
Finally, Section 5, Principal Examiner Insights. Let's get the inside scoop.
Let's move to our final system and see how this all builds together. We're going to build a rock-solid defense against losing marks by looking directly at the confidential Cambridge Principal Examiner reports. The Principal Examiner explicitly states this bold warning. Candidates consistently confuse key terminology. Always define terms before using them in extended responses. Guys, this is absolutely massive. Never ever assume the examiner knows what you mean. And never assume that just dropping a fancy buzzword like Nyquist theorem will earn you a mark unless you actually define what it means in context. If you are going to talk about sampling resolution, you must first define that it means the specific number of bits assigned to each sample before you start explaining how it impacts the dynamic range of the audio file. Clarity of terminology is your absolute first line of defense in the exam hall.
Based directly on those examiner reports, here are the top 3 mistakes that consistently bleed easy marks from candidates across the board. Number 1, forgetting to check overflow and edge cases. When you are writing an algorithm to process sound data, what actually happens if the audio amplitude exceeds the maximum value allowed by your chosen bit depth? That creates an overflow error, leading to digital clipping. Top candidates account for this. Average ones don't even think about it. Number 2, forgetting boundary conditions when testing your sampling algorithms. And number 3, which is frankly the most devastating, writing answers that are not specific to the question's context. If the exam question is asking about sampling voice for a basic low-bandwidth telephone system, and your answer goes on a tangent discussing the high-fidelity requirements of a cinematic orchestra recording, you get 0 marks. Context is king. You have to follow the 3 rules that guarantee top marks: command word decoding, Peel framework application, and time management. To help you retain all of this highly precise terminology under intense exam pressure, here is a fantastic, highly actionable study tip. Create a memory hack. Build a mnemonic using the first letters of key sound sampling terms. For example, for the factors affecting sound file size, remember SR/DC. Sample rate, resolution, duration, channels. You could say, some rabbits dig carrots, or literally, whatever weird phrase works for your brain. Having a quick mental trigger ensures that when you are evaluating a sound encoding format, you don't forget to mention that a stereo file with its 2 separate channels will exactly double the file size compared to a mono file. Memory hacks like this free up your cognitive load during the exam so you can focus all your energy on the analytical depth that the examiner actually wants to see.
So, we conclude today's session with this provocative thought. Look at your last past paper. Are your answers highly specific to the context provided, or are they just a massive overload of raw facts like our friend Alex? Remember to apply this blueprint to your next set of past paper questions. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner.
Ace the exams. Your Cambridge success starts here.